Hello students, the first topic for today will be enzyme kinetics. Enzyme kinetics studies how the rate of the reaction is changed by different factors. The factors may be duration of the reaction or the time of the reaction, the temperature, the pH of the medium, enzyme concentration, and substrate concentration. Why we need to know such of this information? Because there are various clinical significances if we know the changes in the enzymatic reaction for diagnosis, for monitoring, and for prognosis of diseases. The application of enzyme kinetics is used to understand the mechanism of action of inhibitors and activators, and they are used in the production of enzymatic inhibitors for pharmacological control and in drug development. The force dependence is according to the time of the reaction. This is the changes in the velocity of the reaction, and in x-axis is the time of the reaction. At the beginning, the reaction rate increases linearly. The enzyme operates at zero-order kinetics, or independent of substrate concentration. This allows the determination of the initial velocity during the so-called steady-state phase. The initial velocity is measured during the first few seconds using the tangents from this angle alpha, which is formed by this curve and the x-axis in the plot. After substrate depletion or accumulation of product, the reaction rate decreases. For accurate results, kinetic studies are performed only within the initial linear phase. This plot shows the dependence between initial velocity and enzyme concentration. Actually, the reaction rate increases proportionally to the enzyme concentration. This means that doubling the amount of enzyme, for example here, double the reaction rate. Not all catalytic sites are occupied yet. Under equal conditions, the initial velocity can be used to determine the amount of enzyme in the sample. Students, actually, to measure the enzyme concentration could be very difficult, because many times the enzymes are embedded in the membranes, which means to show how many is the enzyme, we need to destroy the membranes to measure the enzyme concentration. That's why in practical we don't use measurement of the amount of the enzymes. Actually, we can understand how many is the enzyme to know how many is the activity of the enzyme, but not the amount of the enzyme. That's why in practical we use enzyme units, which are used to describe the amount, not the amount, but the activity of the enzyme, which means if we know how many is the decreasing of the substrate or the increasing of the amount of the product, and indirectly we can understand how many is the enzyme activity. That's why we use two units in practical. The first ones are international units, which means the amount of the enzyme that converts 1 micromole of substrate per 1 minute under optimal conditions. The second unit which is used is called kTau, which is the amount of activity that converts 1 mole of substrate per 1 second. U per liter, enzyme units per liter, is used in the clinical laboratories for different biological fluids, enzymes that can be measured in different biological fluids or solution, like blood, for example, or solvent. Sometimes, to understand how many is the amount or the activity of the enzyme, is possible when the enzymes use additional cofactor or enzymes are complex ones. These enzymes, for example, if we're talking about dehydrogenases, they can use NAD or FAD as cofactors, and the corresponding reduced forms will be NADH or NADPH. When there is increasing the product of the cofactor, the other name of product of cofactor is coproduct. When there is increasing of this amount, there is increasing of the absorbance of specific light exactly at 340 nanometer of the wavelength. Exactly in this situation, we can understand, according to the coproduct, the enzyme activity in the end. There are many advantages in this method because it's very fast, with high sensitivity. There is the other method to understand, to measure the enzyme activity are direct methods for determining enzyme activity with spectrophotometric and fluorometric measurement. In spectrophotometry can be when there is production of color products, because the color product can accept different lights, and exactly in specific wavelength. For example, like in the previous slide, with a specific nanometer of a wavelength, we can understand how many is the enzyme activity. Fluorometry is another method which is applicable when fluorescent coenzymes are used. Such of this coenzyme is pyridoxal phosphate, which is a derivative of vitamin B6. Exactly, pyridoxal phosphate is a coenzyme with such of this characteristic with fluorescence. The next dependence of reaction velocity is according to the pH, and extremely low or high pH causes denaturation of the enzyme. You can see from this curve that optimum pH is this velocity, this pH, when the velocity is maximal. As you can see from the left and in the right part of the reaction, there is decreasing of the velocity. Why? Because of the denaturation of the enzyme. It's one of the reasons. And one more, it's important to know the pH of the environment, because sometimes the environment has a different of neutral pH in our organism. Do you know how many is the pH in the blood, for example? In the blood, yes? 7.4. Yes, 7.3, 7.4 is a neutral pH. In many times, in many places in our organism, there is such of this neutral pH, but there are some places with acidic pH. Do you know where? Yes? Yes, in the stomach, pH is approximately 2, and the enzyme, which is pepsin, which occurs here, the pH optimum is 2. Do you know places with alkaline pH? In the small intestines, the pH is more than 7.8, around 7.88. This pH is optimal for all these enzymes that we can find here, like trypsin, like all enzymes that are produced by the pancreas, all digestive enzymes. The pH optimum is determined by the change and ionization state of amino acid residues in the active site. One more, the tertiary structure of the protein is important, of course, because do you remember what was important about the tertiary structure? Actually, the tertiary structure is determined by the amino acid radicals. That's why they are important for the pH optimum. And the last one is, as I said, physiological environment in which the enzyme functions. In this figure you can see different pH optimums in the pepsin. We set around 2, and more than neutral pH like trypsin in the small intestines. The pH optimum depends on the charge of the active site or charges in the amino acid residues, interactions with the substrate and any coenzymes, and from the environment. Here are specific examples of pH optimum of different enzymes. Pepsin, around 2, sucrase, 6.2, amylase. There are 2 amylases, salivary amylase or pancreatic amylase, urease, trypsin and lipase, around 8. The next dependence is between velocity of the reaction and temperature. What is this temperature optimum? This temperature when the velocity is maximal. This is the temperature optimum. In our organism, the optimum temperature is between 35 and the maximum is 40 degrees Celsius. More than 40, the enzymes can undergo process called denaturation. That's why when there is increasing of temperature, the velocity of the reaction is increased. Reason, denaturation. But unlike in the low pH optimum, where there is denaturation too, in low temperature, no denaturation. There is just slowdown of the velocity of the reaction, but it's very important to understand that in the 0 or under 0 degrees of Celsius, no denaturation of the enzymes. Just there is decreasing of the kinetic energy in between molecules, but actually no denaturation. One more, if there is more than optimal temperature, and to protect denaturation of our proteins, we have some mechanisms that we set in the first lecture, I think. And don't forget about the chaperones, about the protein disulfide isomerases and prolyl cis trans isomerases, because these are mechanisms to protect the correct folding of proteins and during the denaturation too. That's why the chaperones have one more name, which is heat shock proteins. The next dependence is between velocity of the reaction and substrate concentration. This curve is called hyperbolic and follows so-called Michaelis-Menten kinetics. In this curve you can see some points. The fourth situation is when we have very low level of substrate concentration before the point Km. Km means Michaelis constant. If the substrate concentration is less than Km point, actually this is the beginning of the reaction. The dependence is absolutely linearly. When the substrate concentration is very, very high, we are here somewhere in the right part of the plot, the velocity is maximal, and if we are exactly in the point of Km, or the substrate concentration is exactly in the point of Km, the velocity of the reaction is half of Vmax. The key features of Michaelis-Menten kinetics shows first this equation, which shows in general all enzymatic reactions. In this situation, you can see that there are double-step reaction. The first step is reversible, and there is a combination between enzyme and substrate, and enzyme-substrate complex is formed, which is an intermediate complex. And after this is called association, formation of enzyme-substrate complex. This reaction is characterized by constant K plus 1. The dissociation of enzyme-substrate complex, which means degradation of enzyme-substrate complex, never mind that we're talking about on the left or on the right, never mind. This dissociation of enzyme substrate complex can be to the right to produce product. This means transformation of substrate to the product. This reaction is characterized by constant K plus 2, or dissociation on the left, formation again of enzyme and substrate. This reaction is characterized by constant K minus 1. The reaction is considered in a closed system, no new substrate input or product removal. These are Menten and Michaelis that state everything about enzyme Michaelis-Menten kinetics. This equation is called Michaelis-Menten equation and actually is a mathematical expression of the plot, and shows the dependence between the velocity of the reaction and substrate concentration. Describes the dependence, the same dependence. There are three conclusions of Michaelis-Menten equation, students. To start explain these conclusions, I'd like to return back to the plot. Look the plot again. I said that there are 3 points if we're talking about this plot. The first point, the first situation is when the substrate concentration is very, very low. Remember that. The second situation, when substrate concentration is very, very, very high. And the third situation, which will be the third conclusion of Michaelis-Menten equation, will be exactly what will be happen in the point of Km. Okay, let's see the conclusions. First situation, when the substrate concentration is very, very low. In this situation, under the Michaelis-Menten equation, because the substrate concentration is very, very low, we can miss this indicator, substrate concentration. We can write only Km under the equation. But this ratio between Vmax and Km is constant ratio because both of the indicators are constant indicators. That's why the conclusion will be when the substrate concentration is very, very low, the velocity of the reaction is directly proportional to the substrate concentration, or linearly dependence in the beginning of the plot. Second situation, when substrate concentration is very, very high of Km, what will happen? In the same equation we can miss the Km indicator because it's very, very low. That's why we'll remain only substrate concentration under. But after that, mathematically, we can reduce S and S and will remain only Vmax. Conclusion. When substrate concentration is very high, the equation is reduced to Vmax, which means velocity is equal to Vmax. And the third situation is when the substrate concentration is exactly in the point of Km. What is happened? Let's see. Because they are the same, that's why we can allow to replace Km with the same substrate concentration, S. But S plus S is equal to 2, is multiplied S. After the reduction of S, in the end, the equation will be reduced to half of Vmax. In this situation, the conclusion is when the substrate concentration is in the point of Km or in the Michaelis-Menten point, in this situation, the velocity of the reaction is half of Vmax. Exactly, students, from this conclusion, we can make a definition of Km. What is this Km? Km is this substrate concentration when the velocity is half of Vmax. This is the definition of Km. Comparison between Km and the dissociation constant Kd measures how easily the enzyme-substrate complex dissociates back into enzyme and substrate, because This reaction will be reduced without production of enzyme and product. It's a theoretical value. I'm talking about dissociation constant, and the formula, the equation, will be only ratio between the constant that characterizes the dissociation of enzyme substrate complex, which is chi minus 1, to this one which characterizes the association, the formation of enzyme substrate complex. But when we're talking about the Michaelis-Menten constant, it will be equal to one more additional constant, which is K plus 2, which characterized the next reaction of dissociation of enzyme substrate complex to product. That's why if we want to distinguish this both of the constants, we can say that this one, the Michaelis-Menten constant, usually is greater than the dissociation constant, because part of the enzyme substrate complex is converted to the product in the Km. One more, what they indicate, what is the significance of these constants. If there is low dissociation constant, this means high affinity, and opposite, opposite, high Kg, low affinity. Actually, low Km, constant of Michaelis, generally means high affinity, but also depends on the rate of product formation. To summarize, the Michaelis-Menten constant significance is to show the affinity between enzyme and its substrate, but indirectly, which means that if there is low Km, this means high affinity between enzyme and substrate. Why? Because, students, low Km means that saturation occurs at low substrate concentration. I'd like to go again back to the plot here, yes, this plot. Look, students, when we're talking about the constant of Michaelis, what is this Km? Remember that Km is located here in the x-axis, which means some substrate concentration. This is the Km. When there is low Km, means low substrate concentration. When there is high Km, this means high substrate concentration. If we have low Km and low substrate concentration is needed for the enzyme, this means that enzyme has high affinity to the substrate. Opposite. If we have very high Km, high substrate concentration which means low affinity between enzyme and substrate of the reaction. The substrate with the lower Km is considered the enzyme's natural substrate. The next equation is this one. This equation is called Lineweaver and Burk equation, and is formed after the conversion of Michaelis-Menten equation. Actually, to be easily to determine how many are Km and Vmax, it will be very difficult if we use the hyperbolic curve of Michaelis-Menten, because of this slowdown part of the curve, which is very difficult to understand how many is exactly this point. That's why two other scientists called Lineweaver and Burk, they inverse the equation of Michaelis-Menten, and why? For easy determination of Km and Vmax, because this new plot is like that with absolutely linear dependence. In this situation there will be, and y-axis is 1 to V, the x-axis will be 1 to substrate concentration. Instead of Vmax will be 1 to Vmax, and instead of Km will be minus 1 to Km. Actually, students, you can form this equation alone if you know some mathematics, but very low mathematics. I will show you how to form the Lineweaver and Burk equation alone. Just instead of V will be 1 to V. Then this part down will be up, and this V max is multiplied S will be down. Then Km to V max is multiplied S plus S to V max S. After that, we can reduce S and S, and in the end, 1 to V will be equal to this ratio will be the first, Km to V max is multiplied, this 1 to S plus, and this one will be in the end 1 to V max. This equation is called Lineweaver and Burk equation. You can see here, yes, the same, no, without learning by heart. Application of enzyme kinetics for detection of enzyme defects. Okay, the first application is to understand some diseases. For example, in this scheme you can see the synthesis of purine nucleotides. The purine nucleotide synthesis starts from ribose 5-phosphate. Then PRPP is produced, and then in the end, purine nucleotides are produced in the end, like GMP, GDP, GTP, AMP, ADP, ATP. Okay, these are called purine nucleotides. One of the enzymes, PRPP synthetase, is a regulatory enzyme. This one is regulatory too, but now I'm talking about this enzyme, PRPP synthetase. In this patient, for example, there is only one change of the enzyme. There is decreased Km of this enzyme. Decreased Km. This is the only defect of the enzyme. What does it mean? What does it mean? Low Km of this enzyme. Low Km means that there is high affinity to the substrate of the enzyme. What is the substrate of this enzyme? Look, students, the substrate is ribose 5-phosphate, which means there will be increased affinity with this substrate, which means increased velocity of the reaction and huge amount of products we will produce in the end. Huge amount of AMP, ADP, ATP, GMP, GDP, GTP. But after their this production will be their degradation in the end, but in the end of degradation of purine nucleotides, uric acid will be produced. Which means, remember, we start only from one defect, which is low Km for the substrate. In the end, we have high uric acid in the blood, but high uric acid is gout. This was one of the reasons for gout. Second defect of the same enzyme can be with increased Vmax or maximum rate in some other patients. What does it mean, increased Vmax of PRPP synthetase? Absolutely the same result will be, students. Again, huge amount of purine nucleotides, all this, after that, increased degradation of purine nucleotides and increased uric acid in the end. Again, gout. These were two reasons for gout, only in some defect in enzyme kinetics of one of the enzymes in the synthesis of purine nucleotides. In this table, you can see the conclusions. Now we're talking about this first situations of PRP synthetase with increased Vmax, increased activity of the enzyme, gout, or reduced Km, again increased activity of the enzyme and gout. There are more reasons, but we'll talk about these reasons during the next lectures. Other example are molecular defects in alcohol dehydrogenase enzyme. Actually, this enzyme has 3 polypeptide chains, alpha, beta, and gamma, which are encoded by different genes. In the gene for the beta chain, 3 alleles have been described. Beta 1 with pH optimum around 10, beta 2 with pH optimum around 8.8, and beta 3 with pH optimum around 7. But point mutations, which leads to the conversion to the replacement of arginine with histidine or arginine with cysteine in the beta 2 or beta 3 chains, which leads to the changes in the pH optimum of this enzyme. And in the beta 1 chain, NADH normally, why NADH? Why are we talking about NADH? Alcohol dehydrogenase. Which is the cofactor, students? Which can be the cofactor in general of in all dehydrogenases? Do you remember? There are 2 possibilities only, either NAD or FAD. In this situation, alcohol dehydrogenase works together with NAD. NADH will be produced in the end. This NADH normally in beta 1 chain binds via ionic interactions, which slows its release. It normally slows release. But when there is mutation, such as this replacement of these amino acids, this mutation facilitates the NADH release. Alcohol dehydrogenase activity increases, alcohol is oxidized more rapidly to the toxic acetaldehyde. This will be the result. Here you can see the alcohol as substrate, alcohol dehydrogenase enzyme with very high activity, and this leads to overproduction or accumulation of acetaldehyde. If there is low activity of acetaldehyde dehydrogenase, the result will be the same, because acetaldehyde accumulation leads to vasodilation and increased heart rate or tachycardia, and acetaldehyde is further metabolized to acetate by acetaldehyde dehydrogenase enzyme. But in this case that I explained, there is increased activity of alcohol dehydrogenase, which means rapid accumulation of acetaldehyde. And increased Km and decreased activity of mitochondrial aldehyde dehydrogenase will slow the breakdown of acetaldehyde, and that's why the results will be with accumulation and toxic effect of acetaldehyde after drinking of alcohol drinking. In this table you can see these 3 mutations in beta 1, beta 2 and beta 3 chains with different pH optima. There are 2 forms of acetaldehyde in European people. Both of the isoenzymes, mitochondrial fast migrating form of aldehyde dehydrogenase and cytoplasmic slow migrating form of aldehyde dehydrogenase present. But in Asians, there is absent of the mitochondrial fast migrating form of aldehyde dehydrogenase, which means high affinity for acetaldehyde observed in the electrophoresis. And that's all, everything from this topic.